All right. So this was our last example from the previous lecture. So I tried to introduce the so-called the echelon matrix. So by applying the elementary law operations, so this guy, this matrix has turned to the echelon matrix, which looks like this. And these highlighted numbers, they are called the pivot. And these highlighted variables, and these variables can be associated to each of these pivots, and they are called the pivot variables, right? And also the right-hand side vector changes like this accordingly. Okay, so also you have to remember that in order to have a solution, then this last entry has to be 0. Why is 0? Because this last entry, the last law of the matrix is the zero law. Therefore, this equation has a solution if and only if this last entry equals to 0. Okay. So as far as I remember, the last time I plugged in B1 equals to 5, B2 5, and B3. Sorry, 1 5 5. I plugged in each of these numbers to each of these places, and it turned out UVWY can be written as this vector plus linear combinations of these two. And these V and Y, they are not pivot variables, so they were called a free variables. And so, this guy was a particular solution, and this guy, this vector here, is actually nothing but the null space. All right, so I could say, our null space, it can be generated by these two vectors. These two vectors just next to these free variables. Clearly, these are the subspace of a 4-dimensional Euclidean space. And what is the column vector of matrix A? Column space of matrix A. That is, well, in this case, you can say, span of these 4 vectors is going to be the column space, yeah, which is completely okay, fine. But instead of doing that, I can also say, sorry. I can also say, this guy has a solution if and only if this last condition equals to 0. Therefore, this I can say my column space consists of 3-dimensional vectors B1, B2, B3, such that satisfying this last restriction. Okay, so this is my another description of the column space. All right. Sorry. Even though I have never formally introduced the definition of the dimension, but I keep abusing the word. Sorry about this. Okay. Let me try to study the dimension of the null space of A. What is the dimension of this null space? Well, clearly, this is the null space is a space generated by 2 different vectors, -1, -3, 1, 0, 0, and 1, 0, -1, and 1. So I can say dimension of this null space is 2. Yeah. But instead of just simply saying 2, but I realized that number of these spanning vectors is the same as number of these free variables, right? So is the same as number of free variables of A. Now, how many free variables do I have? Free variable is, well, if any variable is not pivot variable, then we say they are free variable. So then I have 2 pivot here. which means I have two pivot variables. Therefore, I have 4 minus 2 many free variables. So this is, in other words, number of columns of matrix A minus number of pivot. So, okay, good. Now, what about the dimension of the column space? The column space is, by definition, the subspace span generated by each of these columns of A. But using this description, column space is a subspace of three-dimensional space, but with these restrictions. So I try to compute the dimension of CA something like this. So, originally I was in the three-dimensional space, so my degree of freedom was 3, but I have just one constraint or one restriction. And having one restriction means I am losing my degree of freedom by 1. Okay, so the dimension of CA must be 2. Okay, so in other words, 3 minus number of the restrictions. So in other words, number of row minus number of restrictions. But how many restrictions do I have? Okay, again I go on top, and here this y equals to 0 was the restriction, and number of restriction is the same as number of 0 rows in this echelon matrix. Now, how many 0 rows do I have? Obviously, that is the number of rows of A minus number of pivot. Okay. So this is the same as the number of 0 rows in U, which is the same as number of rows of U minus number of pivot. Therefore, this is 3 minus number of pivot, which is just simply just number of pivot. I try to write down everything in terms of number of pivot. Pivot of A. Okay, so generally speaking, for any M by N matrix A, by applying elementary law operations, I can turn A into the echelon matrix. Suppose that I have this looking echelon matrix, and each of these dot represent a pivot of the matrix. This is M, number of rows is M, and number of columns is N. Suppose that I have R pivot, then N of the null space of A must be N minus R dimensional space, right? And the column space must be R dimensional space. So this is NA and CA. Okay. I am trying to write down everything in terms of the number of pivots. And well, so yeah, as a matter of fact, number of pivot of any matrix A is very important from now on. So we will give a proper name for this. The number of pivot of a matrix A is called the rank. And it's denoted by the rank of A. Sometimes just simply RK of A. So this is the definition of the rank. All right. So this, well, from now on, we are mainly interested in the structure or the shape, or sometimes the geometry of the null. For any given matrix A, we are interested in the shape of the null space and the column space. And especially if you're interested in some subspace of any given vector space, then we also need to, we should be able to discuss the dimension. So today I'm gonna give you the formal definition of the dimension. And in order to introduce the dimension, then first I will need to introduce the notion of the linear independence and dependence and the basis. So that is actually the title of today's section. We are on the section 2.3, which is about the linear independence and basis and dimension. Okay. I will define the linear independence. Suppose that I have chosen some k vectors from a vector space B. And we say that these vectors are linearly independent if so this is the definition of linearly independent. So this is somehow very mysterious looking definition. So let me try to explain about this a little bit. Okay, so well, this equation, so for C1 to Ck, so V1 to Vk, they are vectors, and C1 to Ck, they are the number scalars. And linear combinations of this guy equals to 0. So I want to say this is a vector equation. So I have a bunch of vectors, and I want to find the coefficient from C1 to Ck such that satisfying everything equals to 0 vector. So what is the solution of this vector equation? So what choices of the coefficient from C1 to Ck makes this guy equals to 0? Well, the obvious solution is the trivial one. If every coefficient from C1 to Ck, if they are all equal to 0, then this equality is automatically satisfied. Okay, so I say this is an obvious trivial solution. But however, if they are linearly independent, if these vectors are linearly independent, then only possible solution that you can get out of this vector equation is the trivial solution. So if the trivial solution is the all solution you can get out of this, then we say these vectors are linearly independent. But so in other words, if you can find some non-trivial vectors, non-trivial solution or non-trivial coefficient such that everything equals to 0, then they are not linearly independent. Okay. So if not linearly independent, then we say they are linearly dependent. Very obvious naming. Okay, so now we know what do I mean by linearly independent and linearly dependent. If you have never been introduced to the notion of the linearly independence and linearly dependence, then maybe you will have some trouble understanding this. It will be a little bit tricky understanding this. So I will show you some very easy example. Suppose that I have a vector. If a vector W is a linear, if W can be written as a linear combinations of two other vectors, then V1, V2, along with W, these three vectors are they linearly dependent or independent? Linearly dependent. Why? W minus C1 V1, C2 V2. If we move these two terms to the other side of equation, then I have this equation, and clearly, where there is invisible 1 here, so in front of W. So this means, well, this is 1, and which is not 0. Therefore, I was able to find a non-trivial solution such that this guy equals to 0. So therefore, these three vectors are linearly dependent. Okay. Ready to this? Yeah. What about standard unit vectors? This and this and this, they must be linearly independent. Why is that? Because consider a linear combinations of these vectors. C1 plus C2 plus C3. This is what? This is the C1, C2, C3. And we require that this vector equals to 0. In order to achieve this, then C1, C2, C3, they must be all 0, right? So this guy, so this equation implies, so this equation only has the trivial solution. Therefore, these three vectors are linearly independent. Okay. So far, everything was so easy. Now, let me take this matrix. Let me take this matrix. And this matrix has 4 columns. 1, 2, 3, 4. Now, I want to determine if these 4 vectors are linearly dependent or independent. What do you think? Are they linearly dependent or independent? Dependent or independent? Well, actually, this question is very easy. So if you're paying enough attention to these vectors, then you can easily realize that the second column vector is nothing but 2 times of the first. Okay. Okay. And in this case, so 1 times of this, minus 2 of this, plus 1 times of this, plus 0 times third, plus 0 times fourth is going to be 0, right? I mean, if any vector can be, well, if suppose you have some finitely many vectors, and if any of that vector can be written as a linear combinations of the other, then it's going to be automatically linearly dependent. So this is linearly dependent. The column vectors of A are linearly independent. But this time, in this case, maybe my choice of numbers was not very great. Suppose that my suppose that my matrix A has some larger dimensional matrix with even more complicated entries. Then, to determine if the vectors, if the column vectors of the matrix are linearly dependent or independent, it must be way more complicated than this. Okay, so how do you determine any column? So suppose that if any matrix is given, how can you determine the matrices, the columns of the matrix is linearly dependent or independent? That is actually very non-trivial question. So I will try to answer the question from now on. From the easiest one, so from the easiest case, column vectors, suppose that you want to find the linear dependence or independence of columns of some matrix. But this time around, suppose that my matrix is a square matrix and upper triangular matrix. And moreover, it has full set of non-zero pivot. Sorry, I don't actually need to put that non-zero here, because if I say pivot, then that automatically implies that if the number is non-zero. And in this case, the columns of these matrices are linearly independent. Why is that? 3, 1, 4, 2, 1, 5, and 2. So I have 3 columns. And C1, C2, C3 equals to 0. This is the same as C1 times 3, 0, 0 plus C2 times 4, 1, 0 and C3 times 2, 5, 2. Right? Okay. So finding a non-trivial solution, finding a solution of this equation is the same as to find the solution of the system of these equations. And in this case, since the pivots are all non-zero numbers, so C3 must be 0. Therefore, C2 must be 0. And therefore, C1 also has to be 0, right? So C1, C2, C3, they are all 0. So therefore, linearly independent. Okay. Now, suppose that my matrix is not a square matrix and not upper triangle matrix. Then what can you say about the linear independence of the columns of the matrix? Here there is very interesting, well, very useful or very easy proposition, but also very important. I have an m by n matrix A. Then A has linearly independent columns if and only if null space of A is a trivial subspace. Actually, I don't need to prove anything about this. If my matrix A consists of these columns, then C1, A1, da da da, Cn, An equals to 0 is the same as the matrix A times C1 da 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 Cn okay. So that means if you can find any non-trivial solution of this matrix equation, that means this vector equation has non-trivial solution. Therefore, these columns are linearly dependent. Or however, if the only solution equals to 0, so only solution of this matrix equation equals to 0. In other words, if C1 to Cn, if they are all 0, necessarily 0. In other words, that means the null space of A equals to 0, then the only possible solution of this vector equation must be the trivial solution. So this condition and that condition, they are mathematically equivalent. Okay. This proposition gives me some idea. So especially when you're interested in to determine the linear independence of the columns of any given matrix. What about this? Suppose that you have some wide matrix, not narrow matrix, but wide matrix. So number of columns is greater than number of rows. Then in that case, I must say the columns of the wide matrix are automatically dependent. Why is that? Well, yeah, I can try to explain in this way. Well, so to be linearly independent, then null space must be the zero dimensional space. In order to be independent, then this guy only contains the 0 vectors. Therefore, this guy must be the 0 dimensional subspace, which means the number of pivot equals to the number of columns. right? However, if your matrix is wide, number of columns, number of pivot cannot exceed the number of rows, right? Therefore, your number of therefore, null space can never be zero-dimensional subspace. Therefore, the columns must be linearly dependent. Okay, all right. I must write it down. Okay, so to check if an n by n matrix has independent columns, which is the same as the null space equals to 0. And this is again equivalent to NA is zero-dimensional subspace. Then NA being zero-dimensional means number of pivot is the same as number of columns of A, which is n, right? So I told you that this is n minus r dimensional subspace. So in other words, the rank of A must be n. So if n is greater than m, if A is wide matrix, then rank of A is, which is the number of pivot. So this guy can never be m. So sorry, this guy cannot exceed m, but this is clearly less than n, right? Therefore, n rank of A can never equals to n. So this implies A has dependent columns. Okay. All right. Okay. Good. So we talked about the null. So from now on, so we talked about the null space of A. So we discussed how to compute the dimension of null space, and the dimension of null space is very much related to the number of pivots. Now we will turn to the column space. So the question is this: suppose that some matrix is given, then how many independent columns does it have? What is the maximum possible number of linearly independent columns that you can get out of any given matrix A? This is also a very interesting question and very important in practice. And this proposition says the maximal number of the linearly independent columns of A is the rank of A. So if you believe in this proposition, so how many linearly independent column vectors can you get out of A? So, well, in order to answer the question, then first you apply the elementary law operations towards the matrix A. Then you get the low echelon matrix of A, then you know the number of pivot, then that number of pivot that you can have the exactly rank of A many independent columns from matrix A. How do I prove this? So instead of give you the formal proof of this proposition, I will try to convince you by showing you some example of this. A1, A2, A3, A4, A5. Let me say this is my matrix A, and I want to pick, some linearly independent columns from matrix A. How? Let us consider this equation, this system of equations from x1 to x5, everything equals to 0. And try to make it everything into the reduced low echelon form. Suppose that the reduced low echelon form of this matrix looks like this. So this is 1. I have some random another number here, and 1, 0, some another number, and 1, 0, 0. And these three numbers, they are pivot. And I say these columns, and these columns, then the columns that contains the pivot entry, I'm going to say they are the pivot columns. They are pivot columns. For simplicity, I'm going to say R1, R2, R3, and R4, R5. I'm going to name each of these rows, each of these columns from R1 to R5. Now, so the first and third and fifth column contains the pivot, and I want to claim that first, third, and fifth column of the original matrix must be linearly independent. So we want to claim that a maximal set of linearly independent columns of A is the same as pivot column of R. Why? Why is it? So I want to claim the first, third, and fifth columns of the original matrix A are linearly independent. Let me consider this. X1 times A1 plus X3 times A3 plus X5 times A5 equals to 0. Let us consider this equation, vector equation. If the only possible solution of this equation is the trivial one, then I can say that A1, A3, A5 are linearly independent. But you have to remember that this guy was obtained by applying the elementary law operations of this original matrix A. And applying the elementary law operation does not change the solution set, right? So this one equals x1 times r1 equivalent to x3 times r3 plus x5 times r5 equals to 0. Okay. I have just set all free variables equals to 0. If you're setting every free variables equal to 0, so and this solution set is the same as that solution set. Okay, but you know R1, R2, R3, they are nothing but standard unit vectors. Okay, so the only possible solution of this last equation is going to be the trivial solution. Okay, so therefore, the only solution of this equation was the trivial solution. Therefore, A1, A3, A5 are linearly independent. Okay. So, well, so my logic is this. And the null space of A is the same as the null space of R, right? Therefore, null space of this guy intersection with X2 must be the same as right? Because since this guy is the same as this one, right? Therefore, setting every free variables equals to 0, but this set must be the same as this one, okay? But the only solution of this guy was the trivial solution. Therefore, the only solution of this guy, which is this, must be the same as this one. So they must be linearly independent. Okay. So so the column vectors of the pivot columns, they must be automatically linearly independent. Now I want to show you that. So this choice of these, so these are actually the maximal possible linearly independent columns. So in other words, if you try to add just any more columns other than A1, A3, and A5, then they are going to be automatically linearly dependent. Why? Because if you add, well, suppose that you really want to check if A1, A2, A3, A5 are linearly independent or not. In order to check that, then you will need to find the solution of this vector equation, but which is the same as this vector equation, okay? But R1, R2, R3, and R5, they are not linearly independent. Why? Because R2 is merely nothing but some scalar multiple of R1, right? So this guy cannot be, there is some non-trivial solution. So not linearly independent. Okay, great. All right. So this proposition also gives us, not only gives us the maximal number of linearly independent columns of A, but it also gives us, so if you're paying attention to this example, but this proposition also gives us the precise location of linearly independent columns. How you can choose the linearly independent columns from matrix A? How? Suppose that you wanna pick a linear independent columns of matrix A. In order to do that, you will need to compute the echelon matrix of the given matrix. Then the location where pivot column is gonna be where location of independent columns of original matrix. Okay. All right. The next, I want to talk about the basis. What is basis? A basis of a vector space is some collection of vectors satisfying the two conditions. The first condition is V1 to Vk, they must be linearly independent. And condition number 2 is the span of these vectors is the original vector space V. So if these vectors satisfy these conditions, then we say this is a basis. You know, these two conditions are somehow the opposite to each other. So what do I mean by the opposite? So if you have too many vectors, if you have too many vectors, then you're less and less likely to be linearly independent, right? Because if you have too many vectors, then eventually some vectors can maybe a linear combinations of the other, right? So they fail to be linearly independent. But however, on the other hand, in order to span the entire vector space B, then you should have many vectors, right? If your number of vectors are too small, then span of all these vectors may fail to achieve the entire vector space B. So therefore, in order to be a set of basis vectors, then your number of vectors should not be too small, but at the same time should not be that many. So it has to be somewhere in the middle. So these two seemingly opposite conditions. So if you're lucky enough so that you find these set of vectors, then they are basis. These set of vectors is called a basis vector. Okay. I have these two vectors, two standard unit vectors of R3. Is it a set of basis vector? No. Well, obviously they are linearly independent, but well, they fail to span the entire Euclidean space R3 because well, there is no Z component here going on here, so they are not basis vectors. What about this? I have 4 vectors in R3. Is it a set of bases? No. Why? Because, well, in this time around, so span of these 4 vectors is going to be the original vector space R3, but however, they are not linearly independent. Why? Because addition of, well, linear combinations of first, second, and third is going to be, so the last one. So they are not linearly independent. But if I just remove one of the, if I remove one of these vectors, then maybe they are linearly independent. So therefore, they can be a basis vectors. Which one should I remove? Maybe if I remove this, then are they basis? Yes. Yeah. If I just got rid of the first vector, then the remaining 3 vectors, they form a basis vectors of R3. Why? Because linear, well, this vector minus this and minus this is going to be the first vector. So you can get the first vector just by using linear combinations of these 3. So therefore, yeah, it is a basis vector. Or if you like to do, then you can get rid of this one, but you can get rid of that one, and you can get rid of that one. But if you're just getting rid of just one single vector from these 4 vectors, then they're going to be the basis vector. So as you can see from this example, choice of basis vector is not unique. For the same vector space, you and I can choose 2 different set of basis vectors, but they are completely fine, right? Okay. The next theorem, which I consider one of the most important theorem in linear algebra. I have some random vector space. And I have chosen a basis vector. In this case, any vector there is a unique set of coefficient from C1 to Cn such that once a basis is chosen for some vector space B, then it says you can find unique set of coefficients so that linear combinations of V1 to Vn is the vector V. So why I think this is so important? Because of this reason. So well, we are studying the vector space. So what is a vector? So if I ask you some questions like this, then maybe you can try to answer vector is nothing but some tuple n tuple of numbers. Yes, that is not a bad question, but actually vector is even more than this. I mean, everything you can see, you can feel, or you can touch, everything is, well, as a mathematician, I think everything is a vector. And vector is very abstract entity. But, you know, so the random n tuple number is a vector. Yeah, that is correct. But you can think of a collection of some polynomials, or you can think of some collection of, I just can't think of some example. Sorry about this, but collection of some functions or a collection of some points on the space. Everything is a vector, right? So if vector is that abstract, then, but vector is so abstract, but how do you, in order to compute anything, then you need number, right? But vector is so abstract entity, then how do you compute with some vectors? So in order to compute something, then you need a number. And this theorem shows us how to relate a vector to some set of numbers. If you believe in the theorem, then any vector, any abstract entity, abstract vector can be associated to n-2 numbers. Right? Choice of basis means you can have a number. Finally, you have a number. Then after introducing basis, then you can associate a vector to a set of coefficients. Then now you can add or subtract or multiply by some scalar, right? Because now you have number. Yeah. So I mean, having a choice of basis is just exactly the same as the choice of coordinate. So what do I mean by this? So when we were young, so suppose that when you are struggling to prove some theorems in like Euclidean geometry, you need to use some theorems like the SSS or SAS theorems like this. But once you go to the high school, now you know how to introduce the coordinate. So every point is nothing but some two-probe numbers. Then by introducing the coordinate, then you can also play with some geometries, right? Coordinate is very important, very useful tool, useful technique, because you can add or subtract. You have the operations between the coordinate. But however, coordinate is completely artificial thing. If I choose this point to be my origin, and if you choose that point to be your origin, those two choices of origins, those two choices of the coordinate, they are completely both okay, right? But they are both completely artificial. The same is true for the basis. By introducing basis, now and then you can associate the vector to numbers and you can compute. But choice of basis not natural, which is very arbitrary. Okay, anyway, that is so much for the explanation. And I wanna prove the theorem. Actually, this theorem says two different things. Which one? The first one is existence of such a coefficient, and the second thing is such a coefficient must be unique. So I will prove the first part, which is about the existence of the coefficient. But I guess this is clear. There is nothing to prove. Why? Because of the definition of the basis, span of these basis vectors must be the original vector space. Therefore, I must be able to find such a coefficient. So I must be able to write down vector v as a linear combination of these basis vectors. So that guarantees I have such a coefficient. So the proof is done. What about the uniqueness? This is also easy. Suppose that I have two different set of coefficients, and maybe d1 to dn, such that v is c1, v1, c and vn, and at the same time, the same vector v suppose that I have two linear combinations of the same vector v, right? But subtracting the both sides of the equations, then I have c1 d1 v1 cn minus dn vn equals to 0. Okay, but you know that these basis vectors are linearly independent. Therefore, the only possible solution of this equation is the trivial one. Therefore, ci must be the same as di for every I from 1 to n. Therefore, the choice of coefficient must be unique. Okay. Now, finally, I am ready to give you the definition of the dimension. Let V be a vector space and I have chosen some basis vectors. Basis. Then the dimension of V is n. Okay, so this is the definition of the dimension. So what is this? For any given vector space B, I have some, suppose that I have chosen some vector basis vectors, set of basis. The choice of the set of basis can be different. Can be so the choice of the such a choice is not unique, but however, the number of basis vector is invariant. So this is something we call the dimension. So this is definition. The number of basis vector is called the dimension of the vector space. Now, once you give the definition, so in mathematics generally, so in mathematics, once you give the definition, then you have to convince yourself. You have to also you also have to make sure that this definition is well defined. So what do I mean by well defined? Well, I told you the choice of basis vectors is not unique. So for the even if you have the same base with the vector space, my choice of basis vector may be different from your choice of basis vector. But in order to have a well-defined definition, then I also may want to make sure that even though the choice of basis vectors may be different, but number of such a basis vector always have to be the same number, same thing. So I want to make sure of that. So I want to prove this. Suppose I have two different choices of basis vectors. Or the plural of the basis is basis of V. Then M and N, they must be the same number. So even if the choice of basis vectors can be different, but the number of such basis vectors must be the same. How do you prove two numbers are equal? In mathematics, they are very common. The very common trick to prove two numbers are the same thing. So how? Suppose that m is greater than n, or suppose that m is less than n. Well, in those two cases, if I can derive contradictions, then the only remaining option is that m is the same as n. That is the trick that I'm going to use. Suppose n is greater than m. In this case, now for each of these basis vectors, but these are the base, well, for each of these vectors, but v1 to vm, they are basis vectors. So this vector vi, I must be able to write down this guy as a linear combinations of this. I will need to use double indices like v1 v m I v m. Yes, this is right. So wi can be written as linear combinations of these basis vectors. And well, even though I have written down only one equation, but I have n such equations, right? So I varies from 1 to n. So I have n such equations. Well, I want to translate everything in terms of column vectors. So maybe like this. is so considering every vector in the equation is a column vector, then I have this looking equation and this equation can be written as from V1 to Vm, everything multiplied by A1i AMI. Right? Right? So this such a linear combination can be written as a matrix times a column vector. By now, you should be able to understand this. Okay, and I have n such equations, and suppose that I place them everything in parallel manner. Then W1, W2, all the way up to Wn is from V1 to these basis vectors multiplied by A11, AM1, AI1, AIMI, A1I, and or A1 and MN, right? Okay, so I just end up with this matrix multiplication. I want to say this is matrix W, and this is matrix B, and this is matrix A. Okay. What now? Oh, I have assumed that n is greater than m, and this is what? This is m by n matrix. So this is a wide matrix. Matrix A is wide matrix, and I told you if your matrix is wide matrix, then your column vectors cannot be linearly independent. Column vectors must be linearly dependent. Column vectors are linearly dependent means the null space of A has some non-zero vector. Right? So NA is non-trivial. So there is a non-zero vector. This is wide matrix. So there is a non-zero vector in the null space of A such that AV is 0, right? Okay. So W is V times, so here I have W is V times A, but if I multiply this vector to the right of both sides of this equation, then WV is V times AV. But this is obviously zero vector because this is 0, and 0 vector times some other matrix is automatically 0. So W times V equals to 0. In other words, well, the null space of not only A, but null space of W must be also non-trivial, right? because I was able to find some non-zero vector v such that w times v equals to 0. So this is also non-trivial. Is it a contradiction? Oh yes, this is clearly contradiction. Null space of W is non-trivial, means column vectors of W must be linearly dependent. But this is clearly contradiction because we declared that they are the basis vectors, so they must be linearly independent. Okay, so this is contradiction. Okay, great. What now? Now, suppose that n is less than m. In this case, well, I can apply the exactly same trick. In this case, you can set up a matrix equation v equals to w times a, and we can derive the same contradiction. So therefore, n must be m. So in other words, this is an invariant. So I just said word invariant. So what is an invariant? Well, suppose that you want to find some very nice number which is independent of choice of the basis. So choosing a basis method means you introduce some numbers to compute something about the vector space. Okay, but if you can find a number which is completely independent from the choice of the basis vector, then that number must represent some intrinsic nature of the vector space V. So that number we say an invariant. And according to the theorem, I claim the dimension, the number dimension, this is the invariant of the vector space. Because why? Because even though you have chosen two different set of basis vectors, but this number is always the same, right? So this is an invariant. Okay. So therefore, the dimension of the Euclidean space Rn is n, and dimension of span of what is dimension of this? This is 2. Okay, not a big deal. What about maybe this is too easy. This question was too easy for you. Then what is the dimension of this space? These are clearly 4-dimensional vectors. And I am talking about some subspace in R4. Yeah, now things are getting more tricky, but there's nothing to worry about. Oh, yeah, okay, the answer is 3. Because, yeah, the answer is 3. Even though this space looks like spanned by 4 vectors, but the dimension of this is 3. How do I know that? Well, to answer the question, just think of a matrix whose columns are exactly these vectors. Yeah, this guy goes here, this guy goes to there. So I made a matrix consists of these columns, and I apply the elementary law operations so that everything is now echelon matrix. Okay, and I have 3 pivots, right? I have 3 pivots means that the maximal number of linearly independent column is going to be 3. So even though it looks like I have 4 different vectors, but there is only 3 linearly independent columns. Therefore, their dimension is 3. And hey, by the what is that linearly independent columns? I can choose them because I can see first, second, and third columns of the upper echelon matrix is pivot columns. Therefore, first, second, and third column of the original matrix must be linearly independent. So this, if you just drop the last one, then the remaining 3 vectors form a basis of this space. Okay. And sorry about this. And last but not least, I know I just ran out of time, but forgive me. Just give me a couple of seconds. For any n by n matrix, column vector, so column space, the dimension of the column space is rank A. Right? So this is R dimensional, right? And n of A is n minus R dimension. So I'm just repeating the result. So column space is rank A dimensional space, and null space is n minus rank A dimensional subspace. Okay. All right. Great. This is for today, and see you next time. Bye.